Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for the opportunity given to me today. On this occasion, I will present the results of our research with title Honeybee Mating Optimization based Batch Bacon Adjustment for Improving the Fast Rapidly Exploding Random Tree for Global Pet Planning Problem. This research was conducted collaboratively between two universities, Universitas Mercu Buana and Sana University. And this research involve me, Heru Suwoyo, Yingzhong Tian, Andi, Adriansyah, and Julpri, Andika. Here are the contents for my presentation today. First, we are going to talk about the problem statement of global pet planning. Afterward, the brief review of Fast RRT will be delivered. And based on the discussion of Fast RRT, the analysis was conducted and the background, including the objective of this research, are stated. Once the clear objective is stated, the proposed method is discussed. At last, before conclusion is delivered, the comparative results are presented. And here is the problem statement of pet planning. Let X is the state space with n as space dimension. There will be two conditions for this space, which are state space that is already occupied by the displacement of any obstacle, are denoted by X ops, and the state space which is free, no anything lying on it, denoted by X free. The starting and goal point are located on the X free. Then, by referring to the complete information of X ops, the problem of pet planning is to find the way connecting the start and goal point without collision to any obstacle on the environment. Compared to RRT, Fast RRT use improved RRT for finding the initial pet, and instead of generating do sampling until termination criteria satisfied, Fast RRT conduct the fast optimal. It is conducted to optimize the initial pet. Expanding the method of improved RRT, we will have two main strategies performed sequentially that are fast sampling and fast expanding. They replace the conventional strategies of uniform sampling and steer method respectively. But if we expand the fast optimal, we will have pet fusion and pet fine tuning. The original sampling method of RRT is by conducting the uniform sampling. However, this sampling strategy may produce many invalid expansion and result in a large variance in the search time. An example of invalid expansion can be seen from left figure, and the blue area is the figure. In this figure, indicate the explore area of three nodes Q0, Q1, Q2. X-run or random node is the state sampled by the RRT expansion algorithm, and X new is the state generated by steering operation, and then the connection between X new and X run is added as new edge to the main tree by scenario. However, this expansion is invalid because the breadth exploration area of the newly generated node completely falls within the original exploration area and fails to expand the newly explored area. For this reason, the fast sampling was introduced, and the idea can be seen from this right figure. By refusing the sample in explored area, fast sampling can avoid a large number of invalid growth. Right side figure indicates the principle of fast sampling, where whenever we generate random node and it is located on explored area, the process will be repeated by generating the second random node. If it is located in unexplored area, then X new is determined and the connection will be added to the main tree. And this is the more detail about fast sampling strategy. Here, once random node is given by the process of uniform sampling, let's see the algorithm tree. If the random node is generated by uniform sampling and it is located in the explored area, then new X random or random node ray generated by the same method, which is uniform sampling. It is repeated until random node is not in the explored area. And if we would like to know about the position of fast sampling, it is the first step before conducting the other step in the improved RRT. Here is idea behind fast expand. In the complex environment, it is potential to have a narrow channel. Let's see, this is the narrow channel. To ensure that there is no stuck exploration process in the case of narrow channel, fast RRT is also equipped with the ability to adjust the sampling direction, called fast expand or random steering, where this process is same as the improved RRT, which works sequentially with the sampling, fast sampling. I mean, the inside improved RRT we have fast expand that is conducted after we finish conducting a fast sampling. As can be seen from the left figure, if the expansion guide X run 1 fails because hitting the obstacle in the environment, fast expand will randomly generate the direction of theta, which is the angle between x near to x new or x run before when the connection hitting the obstacle. If h, which is the connection between x near and x new, is obstacle free or collision free, then they will be added to the tree. Otherwise, another random state will be sampled by fast RRT. And fast expand enables the random tree of the fast RRT algorithm to pass through the narrow channels quickly. So this one is the traditional way, and this one is after conducting fast expand or random steering. And here are the pseudocode of random steering. If x near obtained by recognition by knowing the near node in the tree from the x run, and the connection between x near to the x new, which is the h, it is collision free, then x new will be registered and the connection will be added to the tree. Otherwise, the theta is generated randomly until x new is located in the obstacle free, and there is no collision if we connect x new to x near to the tree. Whenever we have the connection between x new to x near without any collision, then we add that h to the main tree. And if we would like to know about the position of random steering, is conducted after fast sampling is done. Fast sampling is conducted to obtain x run. Once we have x run, then finding the closest node from the tree, we have x near or near node. Whenever we have x near, then x near and x run become the guidance, the direction for finding x new. And if we have x new and the connection between x new and x near is not collides to obstacle, then the random steer will be repeated. Yeah, the random steer will produce x new without any collision to the obstacle, and this one is the displacement of random steering that is represented by the algorithm 4. Once we have initial path, we from that iteration, the next iteration we call as the previous path, and the previous path found is thought to be processed with the recent path is found. Afterward, the path fusion is then conducted in procedures. It can be seen from the right figure. And the algorithm 5. The intersection between two different paths is initially determined. From the intersection to the starting node, the path cost is calculated both through the Euler path. Let's say the Euler is the green one and the new path is the blue one. Both path, the cost of that path are both calculated from the intersection, and the shortest one is called subpath A. We do same to connect the intersection through the earlier path and the current path to reach the goal, and the shortest one become the subpath B. Combining subpath A and combining subpath A and subpath B, we will have the output of path fusion, and this is the analogy of path fusion, and it can be detailed seen from algorithm 5. And then after we process path fusion, then the next step of Fast RRT is path fine tuning. An iterative process starts from X goal. Let's say that this is X goal and this is X init or starting node. We will check for direct connection with successive parent of each node until the collision-free condition fails. It means that suppose I would like to do path fine tuning from this goal position. This goal position will the connection between goal position to the next the closest node will be checked. If there is no collision, then will be checked to the next node, second closest node, and the third closest node also will be checked. If there is no collision, then directly checking for fourth node. If the collision is detected, or if the connection between the goal position to the fourth node collides to the obstacle, then the connection will maintain the same as the previous. Based on this idea, we will have this connection. And the second one, from the green path and always point contents to this green path. Let's say that we have a new starting node to be checked. From this one to the closest node will be checked. If there is no collision, the next closest node will also be checked. If there is no collision, then the third closest node will be checked. And then if there is no obstacle, then directly the connection to the starting node is become the new edge for path fine tuning. And combine this result, we will have the result of path fine tuning. Path fusion and path fine tuning both are the fast optimal solution after initial path is found. And here is the background and objective of our research. With fast optimal, which includes fusion and path arrangement, fast RRT can be superior in the term of optimality. However, the fusion states will only produce new paths that are relatively suboptimal and decrease the convergence speed. Moreover, path fusion requires the unique path from the previously obtained path, but it is rare when the complexity of the environment is increased, especially when there are more narrow channel. The objective for this research, based on the background, is improving fast RRT with the objectivity of optimizing the fusion stage or even replacing it, and we choose to replace the fusion stage or path fusion. And here is the proposed method. Instead of using the traditional way for optimizing, HBMO is involved. HBMO stands for honeybee method optimization, which is performed to adjust the position of nodes other than goal and start node contained in initial path. This adjustment aims to enhance the optimality of the result, and the best candidate B, which successfully demonstrates the shortest path, is regarded as the queen in the HBMO. This queen will be made with a selected drone. The bees not chosen as queen are considered drone candidates. Using roulette wheel selection, these drone candidates are chosen based on the results of prior fitness calculation. The total fitness across all candidates acts as a divisor for each drone's fitness, resulting in the representation value. This value is utilized to create a cumulative probability distribution. which serve as a reference for simulating the roulette wheel selection. In this model, each individual occupies a segment of the wheel proportional to its selection probability. Assuming the roulette wheel selector generates a random number between 0 and 1, note that yields shorter distance are more likely to be selected as drones. Once a drone is selected, the mating process between the drone and the queen is simulated, involving crossover and mutation. In this study and this research, a crossover process, coordinate values are represented in 8-bit binary form. During the crossover process, superior bits from both the queen and the drone are exchanged using the single point crossover method, dividing the chromosome into two parts. After the crossover point, the relevant segments are exchanged. Following crossover, mutation is applied, involving a bit flipping on the chromosomes of both drones and queens. The outcome of crossover and mutation are referred to as brood. Both entities representing the characteristic of the drone and queen are assessed based on their fitness value to determine which one is superior. If neither exhibits better fitness than the queen remain the same and another drone selection is conducted. This cycle continues until a better brood is produced, which then replaces the drone and queen in the subsequent iteration. The process is repeated 5 times, which correspond to regenerating random nodes in the path optimization space, ensuring that repositioning doesn't diminish the quality of the optimization. Once the termination criteria are fulfilled, another Bacon repositioning occurs. This gradual random reassignment of Bacons results in what is termed the batch Bacon optimization method. This process also stores initial path, where initial path is optimized by applying the algorithm 6, as we can see from this slide. It consists of Bacon nodes connecting starting node and goal node. By implementing the direct connection to the farthest nodes without collision, the number of Bacon nodes in this path is fewer than all nodes present in the initial path, excluding initial node or starting node and the goal node. The number of Bacon nodes is considered a decision variable in the optimization process using HBMO, honeybee mating optimization. A smaller number is beneficial for HBMO's optimization by relocating nodes to relevant areas, limited by a radius R. Decision variable criteria also stipulate maintaining a connection without obstacle collision in the environment, as the path between a Bacon node connection represents the candidate solution. The fitness function calculates the total connection distance from start node to the goal node through the Bacon node. The optimization aims to minimize the search space within a limited time frame. Consequently, HBMO generation aligns with the remaining samples versus the specified maximum sampling. This deployment strategy allows Bacon nodes to shift to new area, potentially connecting directly with other distant Bacon node. The process culminates in another path optimization before determining the final solution. And as we can see, this is the result and discussion for the first environment by performing 3 different methods, which is RRT star, Fast RRT, and HBMO, optimized Fast RRT star. As in this 3 figure, the 3 different methods can properly solve the problem with a sampling time of 1,500. However, the sampling requirement to find the initial path are different from each other. RRT star requires 1,203 repetitive sampling. Fast RRT requires 1,094, and the proposed method is 1,009. This shows that the proposed method is similar to Fast RRT for the convergence rate value. This achievement is logical because the proposed method applies the same technique during exploration, namely fast sampling and random steering. However, referring to the cost path shows in this figure, the proposed method provides better values than two predecessor, RRT star and Fast RRT. This proves that the proposed method can provide more optimal values even though sampling restrictions are allowed during problem solving. As a note, the red bar are the bacon contained by the pad before the optimization is conducted, and the green bar are the representative bacons after HBMO automatically adjust them. According to this duration for all processes, the proposed method is also faster than other involved method. We can see the data from the table as we can see from this slide. Experiments on the first environment are not enough to prove that the proposed method is more effective. Therefore, a second experiment was carried out, and the result can be seen visually in figure attached in this slide. By continuing to use the permitted number of sampling, namely 7,000 times, the performance of the three nodes were compared again. In the second environment, there are a number of narrow channels, and it is mandatory to pass them to be able to explore the area near to the goal point. According to the required sampling time, RRT star requires 6,430 times of sampling to get the initial pad. Fast RRT needs 5,463 times, and proposed method requires 5,346 times to get the initial pad before the pad optimization conducted. The need for larger sampling shows that the RRT star is having difficulty carrying out exploration by relying only on uniformly generated sampling. So it can be said that maintaining the improved RRT, which includes fast sampling and random steering, fast RRT and the proposed method can show better results. Furthermore, the pad generated by RRTs doesn't have sufficient optimality with quite high cost. Meanwhile, in fast RRT, the optimality of the pad is still not enough even though a large sampling has been completed. This is caused by the absence of the rewiring process, which can be useful for determining connection to nodes on the suboptimal, including HBMO, of course. Apart from that, the non-optimal pad is also thought to be caused by the fusion step not being able to run properly due to the failure to get new and unique pad that is better than the previous optimal pad. Even though the pad optimization has been implemented, the final optimality is still lacking and worse compared to RRT star with pad cost of 179 approximately. It might be due to the influence of the previous optimality or no wiring process maintaining the optimality or quality of the previously obtained pad. Meanwhile, for the proposed method in this second case, performance has shown effectiveness with cost pad of 147 approximately at the same number of samples. We can see from this table. Moreover, to gain validity the effectiveness of proposed method, third experiment was conducted. Even though the starting and goal position are replaced on the same position, the complexity of environment is increased. You can see from many narrow channels available in that environment. This complexity is presented by the presence of greater number of narrow channels compared to the previous environment. Referring to this complexity, the number of sampling allowed is 7,000 and the performance is examined in the term of optimality and convergence rate. The positioning of the starting and goal nodes in the third case on the third environment refer to the need to test the exploration process through a narrow channels. The results of this experiment can be seen from the figure attached in this slide. In this experiment, RRT star requires 6,870 times of sampling to get the initial pad. Fast RRT requires 6,136 to find the initial pad, and the proposed algorithm requires 6,090 times of sampling to get initial pad. And compared to to RRT star and fast RRT, the duration and the cost path of HBMO optimized fast RRT, which is our proposed method, is better. So that we can say that our proposed method in this third environment and experiment, we have the better achievement, which are in the optimality and convergence speed. From the results and the comparative result, we have the previous slide. This is the conclusion for our research. With fast sampling, random steering, and fast optimal, fast RRT offer effectiveness in terms of convergence rate and optimality in solving path planning problem. However, path fusion, which is the initial stage in fast optimal, is very dependent on the uniqueness of the new path obtained, so that fusion can then be carried out by involving the previous path. However, in an environment with complexity represented by the presence of narrow channels, narrow alleys, unique paths are rare and may not be available. This becomes even more of a challenge when process rewiring is not provided. So the fast optimal is not strong enough to produce an optimal path. Referring to this, finding RRT star was inserted into fast RRT after the random steering process was carried out. This is intended to support obtaining suboptimal path before optimization is carried out. In contrast to fast RRT, the optimization offered in this paper is the application of honeybee mating optimization with the objective of adjusting the backend position to obtain lower path cost. And referring to the comparative results, and the proposed method can provide better effectiveness value in terms of convergence rate and optimality. I would like to give the highlight for this research. This research is supported by Ministry of Education, Culture, Research and Technology of Republic of Indonesia through the regular fundamental research, and it is supported by Research Center of Universitas Mercu Buana. I think it was all I can present today. Thank you very much for your attention.